This is chapter 19 about blood vessels. And you want to remember that blood vessels are a system. It's a system that delivers all the nutrients, oxygen, hormones, all the things that the cells need. This is the avenue where everything gets there. It's through this system of blood vessels, and it begins and ends at the heart. Arteries are the vessels that carry blood away from the heart. They're all oxygenated except for in the pulmonary circulation and in the umbilical vessels of the fetus. Capillaries have the direct contact with the tissue cells. They serve the cellular needs, and veins carry blood toward the heart. This is a picture that compares what a artery and a corresponding vein looks like. Here you can see that the artery has a much thicker wall. The inside opening of the vessel is called the lumen, and you can see that's smaller than where the vein is here. You see the lumen size is much larger, and the wall is much thinner. And actually, when they cut through this tissue, you can see how the vein sort of collapsed and the artery maintained its shape because this wall is a lot thicker. And this tissue in here is all smooth muscle. So when you look at veins versus arteries, there are some similarities and there are some differences. But they both have the same 3 layers in the wall. And these layers are called tunics. And the word tunic is a covering. So there's the tunica intima, which is the innermost layer. And it starts off with it's an endothelium. And the endothelium is really just simple squamous epithelium. And then above that, they would have maybe some of them as they get larger, a subendothelial layer, which is loose connective tissue. And then you have an elastic membrane. Now you want to keep in mind that arteries are under higher pressure than veins are. So their wall has to be reinforced and they have to be able to expand and contract. And this is in response to differences in pressure when the heart's contracting versus when it's relaxing. So the pressure changes a lot in arteries, and you'll notice that arteries have elastic tissue where veins do not. So you don't see this elastic membrane in the corresponding veins. The middle layer is really important because the tunica media is smooth muscle and elastic fibers, and it has that external elastic membrane, but this is the layer that actually is involved with controlling the size of the blood vessel, the opening in the middle of the blood vessel. So you do have the ability to dilate and to contract. And so this is very important in determining how large or how small that blood vessel is going to be in response to different needs of the body. The external layer is called the tunica externa, and that may be as simple as collagen fibers and very thin, or it could be very extensive in your larger blood vessels. And your larger blood vessels, because the wall is so thick, that actually that wall requires a blood supply, and that blood supply of those larger vessels is called the vasa vasorum. So there's the lumen. You can see the lumen size in the veins is much bigger. The lumen size in the artery is much smaller. And veins also have valves to prevent backflow. And then you see that from arteries to veins, there is this network of capillaries. And capillaries are very simple vessels. They're 8 to 10 microns in diameter. They're composed primarily of just endothelial cells, which are simple squamous epithelium, and they're supported by some connective tissue fibers that's called the basement membrane. Now, this is an overview of the relationship of blood vessels to each other, and also tying in a little discussion on the lymphatic vessels, which we'll talk about in more detail in the next chapter. But from the heart, you have your very large elastic arteries. These are the conducting arteries, and these can be as large as 2.5 centimeters or an inch in diameter down to 1 centimeter. Then they branch into what are called muscular arteries or distributing arteries. And these are the ones that actually have the names that you have to learn in A&P. They deliver blood supply directly to muscles and to various organs. Then you go down to your arterioles, which are your resistance vessels. And these actually feed into terminal arterioles, which will go into your capillary bed. Capillaries are where the exchange occurs, where oxygen and nutrients are dropped off, and CO2 and other waste products are picked up. I'll go through the circulation through a capillary bed in another slide. Post-capillary venules take the blood from the capillaries, and then you go into small veins, which are called capillary vessels, and then back into your larger capillary vessels back to the heart. Now, in the process of dropping off nutrients and oxygen, fluid escapes from the circulation as much as 3 liters per day. So that fluid that seeps out of the capillaries in delivering the nutrients and oxygen is recouped and recovered by lymphatic vessels that surround these capillaries, and that's going to bring this fluid back into the venous circulation, and that's the lymphatic system's major role. Also, it has an immune function, but recovering this fluid so you don't lose it from the circulation is the lymphatic system, and again, we'll talk about that more in chapter 20. So there's 3 types of capillaries, and the first one is called a continuous capillary. Now, continuous capillaries are very abundant in skin and muscles. There's tight junctions that connect these endothelial cells. Remember that those are simple squamous epithelium. And there are intercellular clefts. These are little openings that allow passage of fluids and small solutes. Now, there are continuous capillaries that are tighter than the ones you find in skin and muscles, and those are the ones that are found in the brain. And the cells are more tightly joined together, and they also have the covering of the astrocytes bulbous feet that makes them more resistant to things getting through those capillaries, and that's what they call the blood-brain barrier. Here's a look at a continuous capillary. They have your intercellular clefts, your little openings, and here's the nucleus of this endothelial cell. There's a tight junction. Remember, tight junctions are proteins that link the cells together. And you can see, remember, that your blood cells, red blood cells, almost take up the entire volume of a capillary because they're almost as large as a capillary. Here's your basement membrane, and then on top of that, these pericytes are actually smooth muscle cells that would indicate the beginning of the tunica media if a capillary actually had one. But these are just intermittent. They're found here and there, and they kind of surround the capillary and add a little bit more reinforcement to the structure. Fenestrated capillaries are just like continuous capillaries, with the exception that they have little pores, and those little pores are called fenestrations. So they're more permeable than continuous capillaries, and they can operate in situations where the pressure is a little bit higher, like you would find in the kidneys. So they're involved in absorption or filtrate formation. We're going to talk about these in great detail when we talk about the circulation through the kidney, but you also would find them in small intestines and endocrine glands. There's the fenestrated capillary, there's the little pores, but in every other sense they look just like the continuous capillary. Sinusoidal capillaries, these are also called leaky capillaries because there's fewer tight junctions, they can be fenestrated, they have larger intercellular clefts, very large lumens. The blood flow is very slow. It allows for modification. Cells can come and go through the sinusoidal capillary lining. So large molecules, blood cells, pass between the blood and surrounding tissues. They're found only in the liver, bone marrow, spleen, and adrenal medulla. Macrophages line these vessels in the openings. They can destroy the bacteria. And remember when we talked about blood cells being taken out of circulation by the spleen and the liver? These are sinusoids that are able to grab the red blood cells and pull them through the capillary walls. And also in bone marrow, where cells are being made, blood cells are being created, they have to be able to get through the red marrow out into the circulation, and they can get through these sinusoids. So here you can see a picture where you see the big openings, the fenestrations, very large gaps, and this is why the blood flow tends to be very sluggish going through, and where cells can come and go. Okay, so the capillary beds, this is the microcirculation. These are interwoven networks of capillaries, and they're found between arterioles, which are called terminal arterioles, and venules, which are called postcapillary venules. So there is a shunt that goes through the capillary bed if you want to bypass the actual capillaries in the capillary bed. And usually there's around 10 to 100 capillaries per capillary bed. And the actual capillaries feed the individual cells that surround them. So there's a shunt that if you cut off the capillary network, you go from the terminal arteriole to what's called a meta-arteriole. And the meta-arteriole is continuous with the thoroughfare channel, and that's the intermediate part between the capillary and the venule. The thoroughfare channel goes to the postcapillary venule that drains the bed. So let me show you in a picture form what I'm talking about here. Okay, so here's where the capillary network is open and blood is flowing through all of the capillaries. This is the arterial end. There's your terminal arteriole. And on each of the capillaries that branch off of the meta-arteriole, you'll see this little ring of smooth muscle. These are called precapillary sphincters. Now, when they're open, the blood flows through the capillary bed. But in conditions where, say, you're cold and your fingers are exposed and the temperature drops, to protect the internal organs, these precapillary sphincters will close off and maintain the heat for the internal organs and bypass the circulation to the extremities. And in many cases, if you're not really protected and your fingers aren't covered, you're not wearing gloves, then you can get frostbite. And that's what happens here, because you cut off the circulation to the cells that are fed by this capillary bed. So when the sphincters are closed, you bypass the circulation through each of the individual capillaries, and you go through the shunt I was just talking about on the preceding picture. So you go from the terminal arteriole, meta-arteriole, thoroughfare channel, and to the postcapillary venule, and you bypass the true capillaries. Here, they're open, and all the cells are getting their nutrients. So in frostbite, sometimes tissue will die, turn black, and it can be very painful. So you don't want this to continue for too long. So this is the shunt. This is when the capillaries are open, all controlled by these precapillary sphincters. Now, let's look a little bit at veins. So veins are formed when these venules, from the postcapillary venule, they converge. They have thinner walls, larger lumens compared with corresponding arteries. Blood pressure is lower than in the arteries. They have a very thin tunica media, a thick tunica externa of collagen fibers and elastic networks. They're also called capillary vessels or blood reservoirs because up to 65% of the blood at any given point in time in the body is contained within the veins because their lumen size is larger. Now this is looking at different types of circulation. Now the simplest one is going from an artery to a capillary bed to a vein. That's what we always think of as being the general circulation through an organ or through a tissue. A portal system is different because you go from an artery to a capillary bed, then you go through a portal vein to another capillary bed, then to a vein and back to the heart. Now we had one of these already. We had one of these in the endocrine system when we talked about the relationship between the hypothalamus and the anterior pituitary. In the hypothalamus, we had a primary capillary network. It went down through the from the hypothalamus down to the anterior pituitary through the hypophyseal portal veins, remember? And then you went to the anterior pituitary and then out through a vein. So that's a portal system, and we will find later on in digestion that there is a portal system that takes blood from the stomach, the spleen, the small intestines, through the hepatic portal vein to the liver. Okay, so we'll talk about that later. Then there are vessels that are called anastomoses. And an anastomoses is a bypass, and I usually tell my class, I live in Skowhegan, and we don't have an anastomosis in Skowhegan. If there's a traffic jam, you're stuck. So it's a real advantage to have a bypass. So in this case, you see, here's your capillary bed, but then there's this little shunt that goes around, and that's an anastomosis. Now, veins tend to have a lot of anastomoses, so you don't see as many blockages in veins as you do in arteries, because arteries tend not to have anastomoses, and it can be problematic, and it can cause major problems downstream to the tissues that they serve, like having a pulmonary embolism, or having some type of a myocardial infarct, or a stroke, okay? So they can really have devastating effects. And this is just showing you some combinations, okay? So simple pathway, artery, capillary bed, vein, portal system, 2 capillary beds, and then the shunt is the anastomosis. Now we have to talk about a little physiology involving circulation. And when we think about the term blood flow, you can talk about blood flow through an organ, a vessel, or the entire circulation. Now, we've talked about cardiac output already back in the previous chapter, but it's measured in units, milliliters per minute, and it's equivalent to cardiac output for the entire vascular system. And we talked about cardiac output. We talked about that being stroke rate times stroke volume times heart rate. We said a little over 5 liters per minute. And it's relatively constant at rest, but it varies widely through individual organs based on need. So if you're exercising, blood flow can be diverted to those working organs, the heart, the muscles. And then if you're at rest, then your housekeeping chores can be taken care of, digestion, diuresis, defecation. So that's what they're talking about there. Blood pressure. Blood pressure is force per unit area exerted on the wall of blood vessels by the blood. Now, the unit for that is millimeters of mercury. And it's measured as systemic arterial blood pressure in large arteries near the heart. And that's where that 120/80 comes from, as being blood pressure. That's, the number you've heard of. And pressure gradients provide driving force that keep the blood moving from high pressure to low pressure areas. So systolic pressure is the pressure exerted in the aorta during ventricular contraction. It averages about 120 millimeters of mercury in the normal adult. That's what we're talking about. And the diastolic pressure is the lowest level of aortic pressure, and that tends to be around 80. Now, the term pulse pressure, that variation between the two, between systolic and diastolic pressure, is what you feel as the pulse. And if you take 120 and subtract 80, it's around 40. So mean arterial pressure is the pressure that propels the blood to the tissues. And so this mean arterial pressure is determined by taking the diastolic pressure, which is 80, plus 1/3 of the pulse pressure. And if we said the pulse pressure was the difference between 120 and 80, so you would take diastolic pressure of 80 plus 1/3 the pulse pressure, which is about 13, because 13 is about 1/3 of 40, and that would be about 93. So that's where they're coming up with this 93. So pulse pressure and mean arterial pressure both decline with increasing distance from the heart. So, like I said, if your blood pressure, if you use the values 120/80, then your mean arterial pressure is about 93 millimeters of mercury. And that's the amount of blood, that's the pressure that's needed to supply the tissues. But you can get down to as low as 60 and still have enough pressure to cause proper perfusion to tissues. So there's a lot of variance there. And that finishes up this part of chapter 19.